the first paper that will be presented in this session will be presented by Guowei Liu, and it is about improving MPC ITH with preprocessing. Mask is all you need. The floor is yours.
Okay, many thanks for the introduction. So today I will present our work improving MPC in the height with pre-processing. Mask is all you need. And here is our plan, the background and motivation, a brief introduction to the NIST PQC standardization, picnic, MPC in the height, and the method in 3 steps: reformulate, merge, parallelize, followed by the result and a short conclusion. This timeline shows where our work size, and in the third round of NIST PQC standardization, NIST reached the candidate signature schemes include Delism, Falcon, Phoenix Plus, Rainbow, Picnic, and so on. And ultimately, Delism, Falcon, Phoenix Plus were chosen as the standards. And to broaden the landscape, NIST then launched 2 additional rounds for signature. And in 2024, NIST announced the 2nd additional round for PQC signature candidates. And there are 14 candidates with 6 based on the MPC in the height, such as Park, SD in the height, and so on. Our work targets this MPC in the height family, especially for the picnic family, because it relies on the symmetric primitives and zero knowledge proofs, offering a symmetric primitives alternative. And the security basis of picnic relies on the MPC in the height protocol to build ZK proofs over the NP problem defined by the block cipher LOMIC. And for the key generation, picnic randomly generates the signing secret key as K and the plaintext block P. Then compute C equals a LOMIC encryption of SK and P. And the public key is a pair of plaintext and ciphertext. And also the security, the picnic's security based on this pair. In the zero knowledge proofs, the prover convinced verifies that a given statement is true without revealing any information beyond the validity of the statement. And for the one-way function, LOMIC encryption starts by XORing the first round key with the plaintext, followed by R rounds of encryption. It's a block cipher designed with low multiplicative complexity, and this structure keeps lies and gates, which is exactly what we need for the efficient proofs. Each round consists of a S-box layer and a liner layer, and a constant addition and a key addition. The picture on the right side is the circuit model. This AND gate will represent the S-box layer, and the XOR gates represent the linear layer, and the OR layer represents the constant addition and the key addition. And in the MPC views, the element X is split into n parties, just like this function, X equals X in brackets 1 and plus dot up to the X in brackets n. We should note that the element in brackets is a share, MPC share. Multiple parties PI want to jointly verify whether a secret value X is a pre-image of some value Y under a one-way function F, and in picnic, the one-way function is a LOMIC encryption. So there are some key points we should know. No party learns the secret X directly, and the verification is done using secret sharing and circular computation. MPC in the height turns zero knowledge proofs into an MPC simulation. The prover simulates an n-party MPC commits to all views, and verifier randomly asked to open n-1 views, open the views, ensure correctness, and the hidden view survives witness privacy, and repeat the wrongs, reduce the soundness error. And the picture on the bottom is the workflow of the MPC in the head. The prover generates and commits shares and send this data to the verifier. The verifier using this data to generate random challenge 1 and send back to the prover. And then the prover simulates all the parties of MPC and generates the board values and sends these values to the verifier. And also the verifier generates the random challenge 2. And the prover using this challenge reveals the views. And last step is the verifier to check the values. So our motivation is that needs the PQC standardization sparks interest in non-lattice signatures and picnics with security based only on the symmetric primitives, which means the low mic encryption and the hash function. But there is a pinpoint MPC in the head with pre-processing still incurs redundant computations in practice. So our goal is simple, to make the MPC in the head pre-processing faster in software and hardware without changing the verifier's interface. So here is our method. The MPC pre-processing protocol was proposed by Kazi and his teammates. It reduced the signature size, and it is also known as the KKW protocol. This protocol consists of 2 phases, offline phase, and also named pre-processing phase and the online phase. This MPC protocol is denoted as pi-c, with n parties p1 up to pn. And for each input bit C alpha, a random mask bit lambda alpha is used by this function. The head alpha equals C alpha XOR lambda alpha, and each party pi holds a share lambda alpha I, and by these rules, the sum of the lambda alpha 1 up to the lambda alpha n equals lambda alpha. The lambda alpha 1 means the shares, and the lambda alpha means the mask. The offline phase is independent of the witness W and generates randomness for the offline phase, and also generates compute the auxiliary information for the online phase. The prover generates shares of masks for each party pi, and for each input via alpha, generate shares lambda alpha I. We should note that this alpha only this shares only to the round k wires, and for each AND gate output wires, gamma generates lambda gamma I, and for each AND gate with input alpha beta generates shares lambda alpha beta I, and satisfying this black function, we can see that. And to keep this black function correct, we're using the red one, which means the lambda alpha beta n is not generated by a PRG. It's defined as the lambda alpha XOR lambda alpha 1 x XOR lambda alpha n minus 1 and XOR lambda gamma. And other shares lambda alpha I, lambda gamma I, and lambda alpha beta I for I not equal n are generated by a PRG. And in the online phase, each party's PI evaluates the circuit C with the given values, like that. And for XOR gate, the height gamma equals the head alpha XOR the head beta, and the lambda gamma I equals lambda alpha I XOR lambda beta I. And for the AND gate, the broadcast's values SI is defined as this function, and we can reconstruct it as the sum of the shares SI equals the head alpha times lambda alpha XOR the head beta times lambda alpha, the XOR lambda alpha beta, and XOR lambda gamma. And we can use the mathematical method to obtain that the head alpha, the height gamma equals XOR the hat alpha times the hat gamma. And so far, I showed the classical KKWs split into offline and online phase. Now I will explore the prover's work a bit more finely, where we label the prover's tasks into three phases. The simple phase, and we can say the simple phase only from states we expand all mask shares, and lambda alpha I, lambda beta I, and lambda alpha beta I for I not equals n. And we should note that this PRG expansion only relies on the number of the AND gates and the input shares. For the auxiliary phase, using only these masks, we evaluate the circuit to compute the auxiliary information, lambda alpha beta n. This phase relies on the structure of the circuit. And for the message phase, we combine the masked values with the pre-processed auxiliary information and the witness to produce the broadcast's shares SI. In the traditional view, auxiliary phase takes R rounds, and the messages phase takes another R rounds. I mean the low mic interpretation. That's in essentially 2 full phases over the circuit. However, as we continued our research, we found that offline phase implicitly depends on the witness, so we get an opportunity to reorder and merge. And in signatures, the so-called random tapes is derived from PK, SK message and sort. And the random tape, which means the shares are generated by the PRG, and the SK is the witness. So we can say that the tape implicitly depends on the witness. The traditional 2 phases hide this dependency and lead to 2 practical issues. Redundant work, we evaluate the circuit twice, once to auxiliary phase and once to the messages phase, and miss the parallelism. The way the 2 phases are separated limits our ability to exploit round-level parallels. This operation motivates our next step, merge auxiliary and messages phase to just a single phase can produce the both information, and then leverage mask independence to run all rounds in parallel. I will start with merge, and then show how mask independence gives us round parallel execution. So once we accept that offline isn't truly offline for signatures, we can safely reorder the prover's work. Our first step is merge. Instead of doing 2 full phases, we let the prover run the circuit once with the witness and catch every AND input values. With this catch, this and the masks expanded from the random tape, we produce both outputs at once. Which output, I mean the auxiliary information and the broadcast shares SI. All of this happens in a single compute phase. Importantly, the verify is unchanged, which means the same interface, same checks. We only reorganize the work on the prover side. Now that AOX and messages phase are merged, the natural question is that, do we still have to process rounds sequentially? The answer is no, and here are the 2 facts that makes the parallelism safe. The lambda1, the input mix lambda alpha and AND gates are independent of the output masks lambda gamma. When lambda gamma is derived via the inverse linear layer, together with the masks with lambda O, I showed in this picture. So inputs and outputs do not share randomness. Lambda2, given the random tapes and the to catch the impulse, the alpha, the beta for each round. The compute phase work for that round is self-contained. Therefore, we can execute all rounds in parallel. And on FPGA devices is even clearer. We add a bit of control and registers and benefit from small circles. So we can get that if the mask independence gives us round level parallels. Let me show you what this challenge for in the software, changes in the software and the hardware. And in the MPC phase, we can say for level L1, for security levels L1, L3, and L5, merging auxiliary and message phase into computing phase, bring the MPC time down to about 74%, 81%, 65% of the original, and the parallel down to the about 30%, 32%, 26%. And we can find that the higher the security level, the larger the MPC share in total cost, and the bigger the benefit. And for the end-to-end signing, we can. It also follows the same trend, but the reason why the efficient is worse than that of the MPC stage is that the other parts of the signature have not been optimized. And for the hardware results, we can get a circle reduction from a sequential rounds to a single parallel rounds. And for the AT product, we improved with negligible resource increase. So this is our conclusion. What we get is the remote redundant phases, the auxiliary and messages phase, and we can parallelize across the rounds, and we get a better performance in software and hardware, and a better AT product. And what stays the same is the Wi-Fi. The Wi-Fi is unchanged, and the security argument and interface preserved. That's it. So thank you.
Thank you very much. Any questions? Questions? Can you go to the slides with the tables back?
Which one?
Let's start with this one.
Oh.
The first one. So, in general, you have improved also both in software and in hardware. You have improvements in the compared to previous works, right?
Oh, yeah. So, sorry, pardon. It's too low, the voice. Sorry, pardon.
You said that you have improved both in software and in hardware, the implementations, right?
You mean the real world speed cost? For the original, we tested only the MPC phases in this table. The original MPC phases, and we optimized by the merge and by the parallel. So this is the difference between the second line and the third line.
Okay. Thank you very much. If no more questions, let's thank the speaker again. Okay, then our second speaker is on the stage. So, Thibaut Veneux will present the paper masking friendly post-quantum signatures in the threshold computation in the HAT framework. Please, the floor is yours.
Thank you for the introduction. So Yes, I'm going to present you this work entitled Masking-Friendly Post-Quantum Signature in the Threshold Computation in Z Framework, a long title. So this work has been done by Auguste Varmejanville, co-supervised by Mathieu Rivin and I. And in this talk, I will speak about MPC in Z-based signature. And the idea is that we will try to tweak such schemes to be more masking-friendly. Let's start by some introduction, few elements of context. But the previous talk already introduced the notion of MPC in Z. So has already almost, I guess, everyone knows the history of post-quantum crypto. There is some release signature which has been chosen for standardization. But we need more diversity in the signature schemes in case of a breakthrough in the cryptanalysis for lattice. So the NIST launched a new call for additional post-quantum signature. And we are currently in the second round of this new call. And among the 14 candidates, 6 are relying on the MPC in Z-based paradigm. There was a lot of framework instantiation for the MPC in Z paradigm. The 6 candidates are relying on the recent framework named Volley in Z and TC in Z. And in this work, we focused on the TC in Z framework. So as I said, the goal of this work was to provide some insight of how we can tweak the original TC in Z framework to obtain signature for which masking could be performed with a reasonable cost, computational cost. The equivalent scheme in the context of lattice-based cryptography would be Raccoon, which targets the same goal. More precisely, we try to propose a new MPC in Z-based signature, which can be very efficiently masked to achieve provable disprobing security, meaning that if the value of the variable leaks during the execution of the program, the secret must remain secret. And to achieve such a security, the most used technique is masking. I guess everyone knows, but I will give some element. So instead of manipulating sensitive data during the execution of the program, we will rely on sharing of it. So we will manipulate shares of the value, and shares are random values such that the sum of the value is equal to the secret value. Okay. And so we can make computation on the mask variable. For example, if we are a sharing of x and a sharing of y, we can easily get a sharing of the sum of the two values by having a linear cost in the degree on the size of the sharing. It will be linear in the masking order. And we can make the product also, get a sharing of the product, but in that case, the computational cost of this operation will be quadratic in the masking order. So it would be very easy to produce a masked version of MPC in Z-based schemes. We just need to apply masking everywhere. But since such schemes are relying, there is a lot of field multiplication and bitwise AND gates, it would be very expensive. We will have mainly a quadratic cost. And so we would try to avoid this quadratic cost. To start how we can tweak the framework, I will first present the framework, the TC in Z framework. In such a signature schemes, the secret is usually some vector, a field vector, W, and the public key is, if I simplify a bit, it's a multivariate polynomial in which vanish in W. Then the signature scheme consists in the following. First step, we sample some random polynomial p, such that the constant term is equal to the secret. And we also sample an additional polynomial m for privacy. Then we will commit them using some symmetric primitive, I will more detail later, to obtain some commitment digest. Then there will be an arithmetic phase where we will compute some polynomial q using this formula. Finally, since MPC TC schemes are built from identification schemes where we apply the Fiat-Shamir transformation, we need to compute the Fiat-Shamir challenge simply by hashing the message we want to sign and Q and H. And the challenge will be some set of evaluation points. Finally, the signer just needs to compute the evaluation of the secret polynomial in those public points. And we concatenate everything to obtain a TC-based signature. Of course, it's a bit simplified, a lot simplified. Here is all the steps which manipulate the secret. So if we want to produce a mask version of this signature, we need to mask all those steps. The first step is quite easy to mask since it's just sampling. We just need to sample each share independently. So there will be a computational overhead which is linear in the masking order. It's the best we can hope. The last step is also easy. Since the evaluation points are public, it's the Fiat-Shamir challenge, then evaluating the secret polynomial is a linear operation in the polynomial coefficient. So it's, everything is linear, it's nice. The arithmetic phase is a bit more complex to mask because the public key f will not be linear. It will be a non-linear multivariate polynomial. So this expression will there will be a lot of multiplication on the field. So if we apply a straightforward masking, there will be a quadratic cost. And finally, the commitment phase. In such a commitment, there is several techniques to do it. It will use PRG, hash function, symmetric stuff, and so we will need, if we want to mask this, there will be a lot of AND gate, and it will be quadratic. So we want to optimize this. How we can do? Let's first have a look to the polynomial p, how it is defined. P is defined as a random polynomial of degree L, so that the constant term is the secret. So the randomness is fresh for each signature. And then, finally, at the end of the signature of the signing algorithm, we reveal L evaluation of P. So it means that if, for some reason, we leak any other evaluation of P, we will be able to restore the secret, because we will be able to reconstruct the entire polynomial. So it's not good. It's very sensitive. It's very... So the first possible trick we can do is to change a bit the signing algorithm. We keep the same definition of P. It's a degree L polynomial, a random polynomial. But X does not reveal L evaluation, but only L minus sigma. We introduce some slack. There is a difference between the degree of the polynomial and the number of evaluation we will reveal in the signature. If we do that, then it means that we can reveal sigma other evaluation of P without leaking the secret. And this will be intuitively very practical because it means that we have some sigma probing security by default for part of the schemes. Of course, there is a reason why the signature schemes ask to reveal L evaluation. It's for the security of for the forgery security. And if we do that, of course, it will impact the security, but we can change the parameter to keep the security we want. However, it will increase the signature size, of course. So using this Slack, we will be able to optimize this phase because we know that we will be able to leak some information without any problem. I will not detail more about it, but it's in the paper. I prefer to focus on the second step, which is more tricky which is a bit different to optimize. This tweak, this Slack, will not help to decrease the cost of this step. So we need to find other solution. But first, how we can commit polynomials in TCNZ-based schemes. In fact, there is two methods. The first one is relying on GGM trees. The second is when we rely on Merkle trees. If you have a look to the NIST candidate currently submitted, all of them will rely on GGM tree because it's the technique which produces the smallest signature size. And for such a signature, it's the more important criteria to have the smallest signature. Merkle tree is not used in NIST candidate, but it's used in some zero knowledge proof of knowledge because it's asymptotically better, have better performances. And if we use to produce signature, it will produce a signature between 5 and 10 kilobytes. Okay, let's focus first on using GGM tree, C trees. How we can commit polynomial with such a structure. So we will first expand a GGM tree, so a binary tree for which the two children is expanded from the parent seed using a pseudo-random generator. At the end, we will have n leaves. N is a flexible parameter. And then we will apply again a pseudo-random generator to obtain n field value. We then compute the polynomial delta p using this following formula. And this term, in fact, which involves all the R1, R2, will behave as a mask of P. So we will be able to reveal delta P. The commitment using GGM tree simply consists to commit each leaf seed independently, for example, by hashing them and to reveal the hash digests, and to reveal the max polynomial delta P. Then, to open the commitment, the idea is that we want to reveal all the seed except one. So in fact, we will reveal the sibling path of the red path. And so if, for example, this seed leaks for some reason, it means that the attacker will be able to recompute all the seed. And using this formula, it means it will be able to reconstruct P. So each seed in the seed tree is very sensitive. If it leaks, we fail in the protection. So if we want to mask this, we need to mask every call to the PRG. And there is around 2n calls times tau, which is the number of repetition of the protocol, because it's a sigma protocol. It's a sigma protocol with non-negligible probability soundness error, so we need to repeat. And for typical value, for example, those in NIST candidate, it will be 50,000 calls to PRGs. So if we need to mask them, it will be very expensive. So how we can do in another way? We observe that this tree is used to generate some sharing at this point. So instead of using one tree to generate those sharings, we can use simply one tree per shares. The first tree will generate the first share, the second will generate the second share, etc. And the rest will behave exactly as before. By doing this, we don't need anymore to mask the PRG, because if D seeds leak for some reason, it means that there will be one tree without any leakage, and this tree will will guarantee the privacy. So we have a linear overhead during this masking step, but of course, if we have a D tree, D+1 tree, it means that when we will open it, we will need to open D+1 sibling path in the tree. So it means that we will increase the cost of the opening of the tree by a big factor. So it's not nice. To be more concrete, this is some number on a toy example. The first line is a non-mask variant, where we have a signature size around 4 or 5 kilobytes. And if we mask, and the running time is below 1 second on the Rescue 5 platform. If we don't rely on the tweak, when we will mask the schemes, the signature size will be the same always. It's often like this. But we have the quadratic cost. So the signing time will explode. With the trick, then the signing time remains quite reasonable. However, we have the signature scale with the masking order, and at the end, it's not a very nice signature. Okay, that is the performance with GGM3. What about Merkle tree? To commit a polynomial using a Merkle tree it's simpler. We just need to commit all the evaluation we want to be able to open in the leaves. So we have one evaluation, we will hash it, it will inform the first leaf of the Merkle tree, etc. So if we want to mask this polynomial commitment, we need to mask this step. We want to be able to commit the evaluation from a sharing and to obtain the commitment digest. And for that, we will need to have a mask implementation of the underlying hash function. And so it will be quite expensive. The big advantage of using a Merkle tree is that the tree itself does not contain sensitive data. So no need, we don't need to mask it. Okay, but how we can mitigate the computational cost of masking the first step? In the standard approach, the idea is that we will, to commit a value v, we will hash it to obtain a hash digest, and we need to do that from sharing of v. Instead of committing to the clear value v, we could try to commit directly the sharing itself. Namely, the commitment will be the hash, the concatenation of the hash of all the share. So if we do that, we directly have the deprobing security, because if some value leaks in the D commitment, for the last hash last commitment, it will not reveal the last shares. So it's secure. But there is still a problem. At some point, the verifier will need to be able to open this commitment. It means that the signer will need to provide all the hash inputs. So if we build the commitment like this, it means that the signer will need to put in the signature all the shares. And it is quite expensive to include all the shares in the signature. Hopefully, we have we can improve the tweak In fact, instead of committing to the shares directly, we will compress them into pseudo-random chair. The idea is that there is some existing routine mask compress, which can transform a classical sharing of V into a pseudo-random sharing where D shares will be represented as a seed. And so we have the relation only when expanding the seed. And so we can commit, instead of committing to this sharing, we will commit to this sharing. And when we will need to open this commitment, we just need to reveal V0, but it's the same cost of V, and D seed, which is much, much less expensive. Let's give some number to compare with the previous method. As I said, with Merkle tree, we have a signature size a bit larger than with GGM3. But without tweak, the masking, the signature size is the same. It's independent of the masking order. But we have a big computation overhead. If we use commitment of pseudo-random sharing, it will be much faster, but the signature size increase still with the number of chair with the masking order, but it's much more reasonable than using GGM3. To conclude, in this work, we first observed that masking such a schemes is very computationally expensive. So this issue can be mitigated using some tweaks, which decrease a lot the running time. But the main drawback of this is that it introduces some variability on the signature size. So we can fix an upper bound on the masking order if we want to proceed, like Raccoon. We can combine the slack tweak with the other tweak I show you. This is a figure where there is no tweak here, one tweak here, another, and the combined one. And finally, using Merkle tree leads to better trade-offs than GGM tree because the tree itself does not contain sensitive data, so it's more practical for masking. Thank you for your attention.
Thank you. Any questions?
Yeah, thank you for the presentation. About GGM trees, you said you use D+1 shares, seeds, and if an attacker obtains D leaks, D seeds that are leaking, it's fine. But what if he obtains D+1? I find it strange that the security lies in the fact that it cannot obtain D+1, but D is fine.
So it's one of the formal notion of security in when we make masking. It's deprobing security. So by definition on the model, we assume that the attacker will not be able to get D+1 leaks unless you restart the signature signing, but in that case, it will use fresh randomness. It's a model. It's not perfect, but it's a practical model to make some security analysis. There is more accurate model, like the random probing model. We could try to extend this result in such a model, but it would require a lot of more work. The deep probing model is just a formal model of the attacker, which is quite popular to make some practical proof of security.
Yeah, okay, thank you.
Thank you. It's obvious that your work involves a lot of trade-offs. Can you comment on this? Is there other trade-offs that you haven't considered and that you would?
Yes, of course. The MPC base by nature, such a schemes, there is a lot of trade-offs, there is a lot of parameter. So here is some parameter, but already there is several points for the non-tweak version because we can tweak the size of the tree it's a flexible parameter. I mentioned that we can use, for example, pseudo-random shares, or we need to use masking. But we can make a hybrid version of two. We can use a hash function, which is masked with a low degree order, a masking order, and we combine it with a pseudo-random share. And so there is many possible tricks. We try to achieve some provable security, but if we relax it to have some computational security, we can use some hash technique. It means we hash only the first 12 round of the CHES, for example. There is many trade-offs possible. And yes, I present only some of them.
Okay, thank you very much.
Thank you.
Thank you. Okay, and the last talk in the session will be presented by Katrin Wirschem, and she will talk about all-you-can-compute packed secret sharing for combined resilience.
Thank you for the introduction, and welcome to the talk on all-you-can-compute. Since the 90s, it is well known that cryptographic implementations can be broken by physical attacks, even if the underlying algorithms are proven to be secure. This can be done, for example, by passive attacks, where an adversary could learn some information of the underlying calculation, for example, by measuring the power consumption. On the other hand, we can have active attacks, where an adversary can inject some, for example, electromagnetic pulses to change the values of the underlying calculation in the device. We consider both at the same time, which is called then combined attacks. We also consider the threshold model, meaning that we allow the adversary to have up to T props and E faults. In our model, it is also possible that the adversary learns something from the props before he then faults. So he has somewhat of an advantage to an adversary that can just prop or just fault separately. As we've seen before, masking is a well-known countermeasure to that. Yes, as probably all of you already know, masking means that instead of considering the values themselves together with gates, we now consider somewhat an encryption of the values together with gadgets. So let's look at an example. For additive masking, when considering again T props and E faults and the overall number of shares is n, we would have a secret S, and this is then masked by choosing T elements uniformly at random and one more element Ft, such that the sum of the Fi is equal to the secret S. This gives us already a security against T props, since knowing any T values does not reveal anything about the secret. However, to also be secure against E faults, we would need to duplicate. So instead of doing this operation once and calculating on the shares Fi once, we need to do every calculation at least E+1 times. This gives us an overall number of shares in O of E times T. We can also consider, for example, polynomial masking, where in this case, our secret is set to be the 0th coefficient of our polynomial, and all other coefficients are chosen uniformly at random. Then we evaluate our polynomial at predetermined points, not the 0, to obtain our shares Fi. In this case, we can have n, like the overall number of shares, in O of E plus T. And for the rest of the talk, we will consider polynomial masking. Before I go into more details about that, let's look at the state of the art. So in Crypto 2023, Bernd et al. Introduced the notion of combined resilience for polynomial secret sharing. They also proposed a compiler which considers a multiplication with a very tight number of shares. In last year's CHES, this notion was then extended, and also the compiler was extended to obtain security against two secrets. And very recently, it was a paper uploaded on ePrint, where Arnold et al. Introduced more randomness into the gadgets to circumvent deterministic fault propagation. So they re-randomized everything. In this work now, we consider the state-of-the-art compilers, but adapt them to parallel computation using packed secret sharing. We then prove everything to be secure against our combined attacks, and in the end compare the state-of-the-art compilers in polynomial secret sharing as well as one for Boolean masking to our compiler in terms of randomness complexity and Boolean circuit complexity. All right. Yes, so let's consider first Shamir secret sharing in more detail and then move to packed secret sharing. As I already mentioned, in this case, when we want to be secure against T props, we choose the polynomial degree to be T and set the secret to be the zeros coefficient. Then we choose our coefficients C1 up to CD uniformly at random. We obtain the shares by evaluating our polynomial defined by these coefficients at predetermined pairwise distinct support points. That is not the zero. Yes, the shares then we call Fi here. In this case, we need our overall number of shares to be greater than or equal to D plus E plus 1, where E is the number of faults we accept. This is due to the structure of the underlying polynomial, since if an adversary faults one share, we can see that as an addition of our sharing with another vector that consists one non-zero element. Doing this E times, he can thus obtain at most a vector that has E non-zero elements, which then correspond to a polynomial of degree at least D plus 1, if n is greater than or equal to D plus E plus 1. And thus we can thus see if there was a fault injected just by considering the degree of the underlying polynomial. In our case, I said we want to look at packed secret sharing. So what's that? In this case, we need to make the degree of the polynomial a bit higher. So instead of choosing the degree to be T, we choose it to be T plus the number of shares of secrets we want to have, K minus 1. Then we can set the secrets to be evaluated points of the polynomial, as well as choose some randomness. We interpolate all of this to obtain our coefficients, again, C0 up to CD. And from now, everything is exactly the same as before. We have coefficients, we can interpolate them at our support points x0 up to xn, and obtain the sharing Fi. From now on, to make our life a bit simpler, I will just call this matrix M. And whenever I want to highlight that we consider the secret vector S together with a degree D polynomial and we want to be secure against E faults, I will write the shares as these bracket notation. Okay. We propose several adapted gadgets. For example, the sharewise addition, constant multiplication. For the general multiplication, we have the usual problem we have with polynomials. So whenever we have two polynomials of degree D that are sharewise multiplied, this results in a polynomial of degree 2D. Hence, this is not a valid encoding for us anymore. And we need to do a bit more of work to obtain a multiplication gadget. We also consider a refresh gadget, which basically just means we have a sharing of, let's say, a vector A, and then we change the underlying randomness of this sharing, but it still remains a sharing of A. And last but not least, we have the linear transformation gadget, which we can use, for example, for the permutation in AS. Okay, let's look at the multiplication in a bit more detail. We propose two multiplication ways. One of them is called BGW-based multiplication, because we first do a sharewise multiplication, obtain a polynomial with respect to degree 2D, and then do a degree reduction to obtain a polynomial with respect to degree D again. doing this, to not lose any information in the middle, we need to have at least 2D plus E plus 1 shares. Bernd et al. Proposed another multiplication called Laola-based multiplication to obtain the tight number of shares. It's kind of the same thing, but the other way around. So there, they first do the degree reduction, then do some sort of share-wise multiplication, and combine everything together to get a valid sharing again. For now, let's consider the BGW-based multiplication. Yes, you can see here the pseudocode, and as I mentioned, that's basically just a share-wise multiplication together with a degree reduction, where our degree reduction consists of a refresh, which is denoted here as the 0 encodings, and later the addition of the 0 encodings to the things we compute, together with a matrix multiplication, which is here the multiplication with the matrix lambda. This degree reduction matrix is built as follows. It first unmasks with respect to the degree 2D polynomial, then remasks with respect to a degree D polynomial, and adds some randomness. Notably, these m's are public values since they only consist of the support points which we consider to be public. And also, the re-randomization matrix is only built from uniformly random elements together with the information we have in M. So we can perfectly simulate this construction for the degree reduction. So now let's consider a bit more about the security. So in a nutshell, problem resilience comes due to the following. First, we have share-wise operations. So we can use everything we know about the underlying polynomials. Then we have that the 0 encoding is perfectly simulatable. This is due to also the support points being public values, and we have freshly generated randomness which can be simulated. The degree reduction can be simulated as well, as I just mentioned, and in the end, we re-randomize. Like we have this refresh step after the nonlinear layer, which is the matrix multiplication. Yes, this is due to the addition for the 0 encodings. Notably, in our proof, we upper bound this. So whenever there is a prop in the 0 encoding construction, we just reveal all shares for this 0 encoding. For the fault resilience, we also rely on the underlying polynomial structure, and we get this fault propagation through the random part of the matrix lambda. So whenever we have a fault, this random part is triggered, meaning that all shares and all coefficients are re-randomized, giving us a random polynomial of degree n. Last but not least, we wanted to have combined resilience. And we obtained this by having the probing and the fault resilience together with something more. And something more is that we say, okay, it needs to be possible to push any injected fault to the input, the randomness, or the output. And this we again obtain due to the share-wise operations as well as the construction of our degree reduction matrix, where basically whenever a fault is injected to the construction of this matrix, this propagates at most column-wise, which then results in just one fault in the output. Okay, so let's consider why do we look at this at all. Parallel computation is useful whenever we focus on the same computation on different secrets, for example, when considering block ciphers. So on the right-hand side, you see a nowadays common block cipher structure. We add some key, we have some substitution box followed by a permutation, and then we do this several rounds. So having then the possibility of having k secrets in one sharing, this compresses the computation. So for example, for AES, we can put 16 secrets into one sharing and do not need 16 sharings anymore. So yes, we get reduced computational and randomness complexity. Now we wanted to compare our solution to some previous works. So we have here the BGW-based compiler, the Laola-based packed secret sharing compiler, the previous Laola with one share, the double sharing, also the Laola part, as well as CineMinis, which is a Boolean masking scheme that is also secure against combined attacks. Yes, and here you see one round of AES 128 with T props and E false, and we consider always T is equal to E, which is whatever is written on the x-axis here. We have on the left side the randomness complexity, and on the right side the Boolean circuit complexity, where for the randomness complexity we're kind of comparable to CineMinis, and in the Boolean circuit complexity we're better than CineMinis. You might wonder why they escaped so fast at some point. This is due to the need of error correction after each multiplication. For us, it's sufficient to have one error detection at the end due to this re-randomization. All right, so that's nearly it. So let's consider the summary. So we showed an efficient approach for combined leakage and fault resilience using packed secret sharing. So doing this, we extended the state-of-the-art gadgets and gave a detailed security analysis. What's next? Of course, we would like to further reduce communication and randomness complexity and implement everything to get a practical evaluation. Thank you very much.
Thank you. Any questions? Yes.
Hi, thank you for the presentation. So I'm not as familiar with this particular secret sharing, but I'm familiar with polynomial masking. And for polynomial masking, every time that you are adding a share, the SCA security was degrading because the SCA attacker can use all those extra shares to reduce the number of traces. Is it also the case for this particular sharing that you're using, or do you have less of this effect?
We have a similar effect until we refresh. So whenever we refresh, we reintroduce new randomness, so previous shares are not able to be used anymore.
Yeah, but for a single operation, for example, if you have like 2D probe, then like the number of traces will go down by a lot. Okay, thank you.
Any other questions? I have a question. What about CIFA? Is your gadget secure against CIFA?
Yes, due to this re-randomization of all the high order coefficients, we do not have the secret in any coefficient except for really the coefficients we put it in, which is not directly visible in the sharing. So yes, we can show that we're secure against this.
And you left as future work the implementation. Do you think it's feasible? How big will this implementation be?
We currently work on a follow-up of this for a software implementation, and so far it looks pretty good. So
which cipher do you implement?
Sorry?
Do you implement a specific cipher, or just you implement the gadgets?
The gadgets, yes.
Ah, okay. And hardware implementation is not on the table in any way?
Not that I know of.
No? Okay. Thank you. Any more questions? If not, thanks to all the speakers of the session. And please